Good morning, chemistry students. Today we're going to continue our discussion on the gaseous state of matter. And part of what makes the gaseous state of matter so interesting to talk about is its history of discovery. Um, Over the past several hundred years, going back to the 1600s, um, the gaseous state was fascinating to scientists because, first of all, the air around us is invisible and yet we know that it's there. And something else is that it's actually kind of complicated. If you think about it, there's lots of variables that gases have that you can kind of change up, and they all seem to be connected to one another. So, for instance, we've been talking about the fact that gases exert pressure, but they also occupy volume. Okay, so the amount of space that the gas sample takes up. Gases fill their container entirely, and that's pretty interesting. That's different than solids or liquids. Right? If you've got a cup of water, the water's sitting at the bottom of the cup or wherever, however much it can fill up the cup. But if you have a cup filled with some type of gas, like air, the entire vessel is filled with it. Okay, so if you go to the far corner of the room you're sitting in right now, you're going to be sure to find some air in that far corner because gases spread out and they fill their containers. So they have volume. They take on the volume, the entire volume of their container. Um, Gases also have temperature, okay, right? Just like everything else, all matter has a type of temperature. Uh, and something that was not obvious in the past, but became more and more obvious, is that gases are made up of molecules. They are made up of particles. And we can count up the number of particles using the concept of the mole. Okay, so gases exert pressure, they occupy volume, they have a temperature, and fundamentally, they are made up of small molecules or atoms, and we can count that up in the moles unit. Okay, so um, we're going to focus in on a couple of the gas laws today, and the first one to talk about is Boyle's law. Boyle's law is named after a very famous scientist. He's an Irish scientist named Robert Boyle, and here's the Wikipedia page on Robert Boyle. Okay, so um, a lot of these guys in these paintings that they made of folks, they don't have like a big smile on their face, and that's because they had to pose for their paintings normally. Although the artist might give them a smile at some point later on, but Robert Boyle is considered by many to be one of the pioneers of the scientific method. And part of what makes the scientific method is to have a controlled experiment. And so Robert Boyle, when he was thinking about experimenting with gases, he realized that they could get kind of complicated. So he focused in on two variables, pressure and volume. And he realized he had to hold the temperature constant. So he had to hold that constant. And even though he didn't quite realize it, he ended up holding the number of moles constant as well because he had a fixed sample. Kind of locked it in and sealed it up. And so when he did that, he was locking in the number of gas particles in his sample. So in a good controlled experiment, it's important not to let things get too complicated. Otherwise, you don't know why your results are what they are. For instance, if you're trying to grow some plants and in one pot you put one type of plant and you give it plenty of water and sunshine and fertilizer, and then in a second pot you have a different kind of plant and you don't give it as much water and you don't give it as much sunlight and you don't give it fertilizer, and then you try to compare your results, you're not really going to know why you're getting what you're getting. You'll kind of know why. You'll know you've changed a lot of things, but you won't really be able to know the contribution of each one of those things. How important is the fertilizer? How important is the water, etc. So having a controlled experiment was really important for the development of the scientific method. Okay, it was all about controlled experiments, and then you could make an inference about why things are happening. Okay, so a little bit more about Robert Boyle. Like I said, pioneer for the scientific method. He's also considered to be one of the first chemists. Um, he is right there on the boundary in history between the alchemists, who had some mystical ideas about turning elements like lead into gold, and something called the elixir of life, and things like that. Um, with modern chemistry, with Antoine Lavoisier in the 1700s. And so he's sort of sitting right there on that boundary between the alchemists and the chemists. And so um, he ended up actually writing a book called The Skeptical Chemist, and it's spelled a little differently than we spell it today. They didn't really have official spellings back when Robert Boyle was writing, not to my knowledge. But with that book, he is credited as being one of the first actual chemists. And he's really well known for a law called Boyle's Law. So we're going to talk about Boyle's Law right now. So Robert Boyle, he was a wealthy aristocrat. Like a lot of scientists back several hundred years ago, it wasn't common people that were out there doing controlled experiments, and lab equipment tends to be pretty expensive even today. And so it tended to be people of means that had the money and the time to do science. But he had, from what I remember, he had kind of a large house, and he set up a really tall device in the foyer of his house. I think it was right there in his front door as you'd come in. It was a really, really tall U-tube. And so it kind of looks like a cane, but this is actually a tube. And I think it was several yards tall. Okay, and this was a glass tube, and it was open at the top. And what he did is he suspended this from his balcony, or kind of had it there in the front of his house because it was that tall. And he poured in some mercury. Okay, so he poured in some mercury, and the mercury came to the bottom and started filling it up from the bottom, kind of pooled there. And after a certain point, it traps a sample of gas over here. So this right here becomes trapped air, basically. Okay, and so what that is something called a fixed sample. Right? If you think about it, if you believe the idea that air is made up of a bunch of molecules, really, really tiny molecules, and you kind of trap it, you've locked into place the number of molecules that would be in there. Boyle didn't really think about it this way, but that's what he was doing. So he's locked in the number of moles of gas. Now, something he did realize is he wanted to keep the temperature constant, because he realized temperature might affect what he was doing. But anyway, so he poured in some mercury. And what he started doing was, after he would pour in some mercury, he would measure the pressure and the volume of his trapped sample of air there. So right now, it would be really close to atmospheric pressure, okay, because the mercury is at the same level on both sides. So almost certain that he had a barometer, and so he was able to know what the pressure was at that moment. Okay, so he had a barometer somewhere else in his house nearby, and so he knew what the atmospheric pressure was. Okay, then he kept on adding in more and more mercury, and he would take more measurements. So pour in a bit more mercury. Now this time, if you pour in some more mercury, that gas starts getting compressed, but it kind of pushes back a little bit harder than on the other side. And so you start to get some unevenness at that point, okay? Because that pressure is kind of building up over here. And so he would pour in some more mercury, measure the new volume, and now he could determine the pressure based on what we were saying the other day in the context of manometers. Here we have a little height of mercury that's different on each side. So we have the pressure due to the mercury, and we also have atmospheric pressure pushing down. So we have those two pressures kind of pushing down here. And on this side, it's just the pressure of the gas. And so he's able to measure the pressure of the gas. And he continues doing this over and over and over again, taking down some data. Okay, so we pour in a little bit more mercury and measure the pressure. You know, this one would go up a little bit, right? Something like that maybe. And so he would continue on, and he measured sets of pressure and volume, pairs of data like that. Okay, and he discovers something kind of interesting. Think about it: the more pressure we apply on a gas sample, the less volume it's going to occupy, right? Okay, more pressure, smaller volume. More pressure, because there's more mercury there, right? It weighs more. Smaller volume. Okay, so let me actually draw the graph the way I normally do. I should have looked more carefully earlier. The more pressure, doesn't matter what the unit is, could be atmospheres or millimeters of mercury or kilopascals. The more pressure we apply, the smaller the volume. Okay, and so Robert Boyle, he actually noticed something interesting about his data. What he saw was that if you took any of the pressures that he measured, maybe it's this one right here, if you took any of the pressures and you multiplied it by the volume of that gas at that particular moment, so some particular volume there and some particular pressure here, what he saw is that pressure times volume is a constant. All throughout the course of his experiment, whenever he would measure pressure, some new pressure, and you'd get some new volume, he saw that that was always a constant. Okay, and so you could call that one pressure 1 and pressure 2. You could call this one volume 1 and volume 2. As long as you had pressure 1 with pressure 1 with volume 1 or pressure 2 with volume 2, you always got some constant. Okay? As long as you were using the values from along that curve, it was a constant value. And this is what is known as Boyle's law. Pressure times volume is a constant, provided you're holding temperature constant and you have a fixed sample of gas. If you change those, you might not be able to discover this relationship. And so that was sort of what Robert Boyle had to do to make that discovery there. All right, this makes sense. If you have a high pressure, you can kind of compress the gas sample down. But the whole idea is less pressure, more volume, right? Less pressure, more volume, same type of thing, right? If you have less pressure moving along this curve, you get a greater volume, okay? And then more pressure, less volume. So that's Boyle's law. One of the more interesting applications of Boyle's law is to take into account these sets of ordered pairs here. And since pressure times volume is always a constant, it doesn't matter whether it's the first pressure and volume or the second pressure and volume. You're always going to get a constant. And that leads to a more convenient form of Boyle's law that people can use to solve problems. P1 V1 equals P2 V2, and that's because they both equal some constant. So let's see how this works in a couple problems for Boyle's law. So you have a container, it has 500 milliliters of carbon dioxide, 20 degrees Celsius, 742 torr. What will be the volume of the CO2 if the pressure is increased to 795 torr? Okay, so something to recognize in Boyle's law is that if pressure goes up, volume is going to go down. And if pressure goes down, then volume is going to go up. This is called an inverse relationship. Inverse relationship. So if we have more pressure, we're going to increase the pressure. What's going to happen to the volume? The volume is going to drop. We're in that first case, right? So let's list out pressure 1 and volume 1. Let's list out everything we know about this gas here. Pressure 1. That first pressure is 742 torr. The first volume is 500 milliliters. The second pressure is 795 torr. And we're going to figure out the new volume. Okay. They've given us the temperature, but we should assume that the temperature is going to be constant, as is the sample. So we're not going to add in extra gas particles. So let's plug in what we have. So P1 is 742 torr. First volume, 500 milliliters. Second pressure, 795 torr, along with V2. To solve that equation, we want to divide both sides by 795 torr, and that'll give us V2. So in the calculator, I'm going to type in this fraction to find V2. So 742 times 500, that would be P1 times V1. So there's our constant value. And now we're going to take that constant value and divide it by the new pressure, 795. Okay, so now we have our new, that doesn't seem reasonable. Let me go back and type that in one more time. I need to do 1400 divided by 3. Control Enter. There we go. 466 is the new number of milliliters. Okay, that's reasonable. A little bit more pressure, a little less volume. So that's the idea behind Boyle's law. In Boyle's law, the units don't actually matter. I think the units that Robert Boyle was using at the time happened to be a pressure unit called inches of mercury, and the volume he was using was cubic inches. That's right. But it really doesn't matter the units that you use. Boyle's law is always going to hold regardless of the units. So when you're solving a Boyle's law problem, you can have units of whatever, liters, milliliters, gallons, any unit for volume works, any unit for pressure works, provided you're using the same unit on each side of the equation. Whatever unit you have for P1 should be the same unit as for P2. Whatever unit you have for V1 should be the same unit for V2. Okay, but as long as that's you're sticking with that, you can solve these problems. So for today, I would like for you to focus on solving the rest of these problems here. 2, 3, 4, and 5. And then tomorrow on Tuesday, I'll provide a key so you can check your work.